which is packed in just a few grams of material. Metal organic frameworks have been used in a wide range of chemical applications. By varying metal ions and ligands, you can get a various number of combinations of MOFs depending on their application. So they can be used for gas storage, gas separation, catalysis, sensing, drug storage, and delivery. Metal organic frameworks have the highest carbon dioxide adsorption capacity known to the man. They can be specifically engineered to target carbon dioxide even in humid conditions. The pioneers in the designing and developing metal organic frameworks are Nobel Prize laureates from last year. They're Susumi Kitagawa, Richard Robinson, and Omar Yagi. They have synthesized and developed a huge number of metal organic frameworks, from which I would highlight CALF 20, which is presented on the left side. It is MOF with a large capacity to absorb carbon dioxide. It is suitable for large-scale applications and has also low-cost production. It is super stable adsorbent for carbon capture and storage even at humidic conditions. The second MOF, which is labeled MOF 330 in the middle, is MOF that can capture water vapor from desert air at the night. It also can release this water afterwards during the day. So we are living in the era of water bankruptcy, so it is very important to have material that can absorb and release water in huge amounts. So this MOF is synthesized by Omar Yagi in the large scale production in the kilogram scales, still not in the ton scales, but the procedure can be developed further. The third MOF is MOF that can absorb and release hydrogen under atmospheric pressure. This is the first MOF that we have used for our simulations. It is MAF label 66. So it is zinc triazolate MAF, which is an imidazolate type ligand that possess, and it has high porosity and contains uncoordinated amino group and azolate nitrogen donor with high gas uptake and remarkable gas absorption selectivity. We choose this MOF because it is good absorber for carbon dioxide, and there are a lot of experimental data that help us to develop force field parameters as a starter for the designing a new MOF that are still similar to MOF 66. On the right side are some experimental data on the absorption of carbon dioxide and methane. And then we go further and also perform simulations of carbon dioxide inside the CALF 20 Calgary framework that I mentioned and that was highlighted at the Nobel Prize level. It is MOF with high capacity and selectivity for carbon dioxide, and it is a promising candidate for large-scale carbon dioxide capture due to its good sorption performances under industrially relevant conditions. Before I discuss Grand Canonical Monte Carlo simulations in details, I want to show you the overall of molecular simulation workflow. Here we start. Here you can show that see that we start with input for MOF simulations. The Inputs are the crystal structure of MOFs, for example, are MOF 1 that presented here, or MOFs or hosted gases like carbon dioxide and methane. Then, as an input, you need force fields to describe these interactions. In the next part, we apply simulations which are based on the statistical mechanics. And this work, we mainly use grand canonical Monte Carlo simulations, but someone also can use molecular dynamics simulations. And as an output, you can get from these simulations adsorption isotherms, diffusion coefficients, and you can extract some snapshots from the molecular dynamics or grand canonical Monte Carlo simulations to go into details about the adsorption mechanism. Here in this graph is presented the potential energy surface. Potential energy surface represents the energy of a system as a function of the positions of all atoms. We can think of it is like an energy landscape containing hills and valleys and many local minima. In molecular modeling, we are generally interested in finding low energy structure because this corresponds to the most stable and physically relevant configuration. The deepest point on the surface is called the global minima, which represent the most stable structure. However, many other local minima may also exist. The challenges is that for complex systems such are MOFs and adsorbed molecules, the potential energy surface is extremely high dimensional and contains a huge number of minima. Therefore, efficient search techniques are required. Here are some of the common conformational techniques that can be used for finding the minima. They are energy minimization, molecular dynamics, and Monte Carlo that I already mentioned. One of the simplest methods for exploring the potential energy surface is energy minimization technique. The idea is to start from initial configuration to perform some mathematical optimization algorithms and to adjust which can adjust the atomic positions to reduce the total potential energy of the system. We can think of this process as a ball rolling downhill on an energy landscape until it reaches the minimum, which corresponds basically first the local minimum. In adsorption studies, energy minimization helps us to identify the most favorable adsorption sites inside the MOFs. The adsorbed molecules the adsorbed molecules on the right side moves toward regions where its interactions with the frameworks are most attractive and where the potential energy is the lowest, as usual. So for gases such as carbon dioxide, methane, and nitrogen in many MOFs, these attractive interactions are dominated mostly by van der Waals interactions, although electrostatic interactions can also take account and important role when the framework contains some charge or polar groups. But besides this technique, more advanced techniques are molecular dynamics, which is based on Newton's law of motion. It generates a trajectory in the phase space and determine time dependent evolution of the motion of molecules. Monte Carlo techniques are also advanced techniques. They are based on probability of energy change between different conformations, and they can calculate some mean values of the system of interest. So Monte Carlo simulations are developed to overcome some of the limitations of dynamical atomistic calculations. Instead of integrating the equation of motion, Monte Carlo performs a random walk to measure properties of the systems. The Monte Carlo technique is of general use, and it is not limited to molecular simulations. It has potential of being more efficient than molecular dynamics for simulating MOFs. So we do not need to follow the natural MD dynamics of the system. We can even do some unphysical trial moves like identity changes, insertions at a random position, changing the connectivity, etc. Whereas molecular dynamics is an alternative approach to Monte Carlo in simulating MOFs by sampling the phase space, but provides also full dynamical information and can model processes that are characterized by extreme driving forces and that are non-equilibrium processes. Monte Carlo cannot do this. So for the long trajectories, molecular dynamics can coincident to Monte Carlo simulations based on this ergodic hypothesis. An ensemble average of an observable is equivalent to the time average of the observable. So for the longer trajectories, these two methods can coincide. Now I would like to mention some ensembles that can be used to model MOFs. What is an ensemble? Ensemble is a collection of points in a phase space satisfying the conditions of a particular thermodynamic state. One of examples of ensembles are microcanonical ensemble, label NVE, canonical ensemble, label NVT, isobaric isothermal ensemble, label NPT, then grand canonical ensemble that we use for our simulations, or you can choose your own ensemble. This is one example is canonical ensemble, which is a collection of systems with the same number of molecules that occupy the same volume and that are at the same temperature. We used mostly, as I said, grand canonical Monte Carlo simulations for our work. Monte Carlo conformational search methods are used to find stable configurations of molecules, making random changes to the system, such as random changes in Cartesian coordinates of a molecule. After each change of the trial configuration, its energy can be calculated. The change is accepted or not according to the conditions of the Metropolis algorithm. In grand canonical ensemble, as I already said, the temperature and chemical potentials are imposed and the number of particles is allowed to fluctuate during the simulations. The grand canonical Monte Carlo method can be used to determine the adsorption isotherms, where the pressure in the reservoir is related to the chemical potential given with this equation, and here F is fugacity. Which is activity of the gas and has the same units as the pressure. This is the Metropolis algorithm based on which acceptance rules for insertion and deletion of particles in the grand canonical ensembles are based. And here, if accepted, then go to the displacement operation. Otherwise, go back and calculate energy probability for the displacement of a single particle as with the probability which is given with this equation. Here, V is the volume of simulation box, lambda is the thermal de Broglie wavelength, Kb is the Boltzmann constant, T is the temperature, and En or En plus 1 are the internal energy of the configuration with the N or multiple N plus 1 adsorbed atoms. Steps in performing Monte Carlo simulations are to select one interaction model, then to select the boundary conditions, selection of initial position, selection of ensembles, NVE, NVT, or NPT, selection of target temperature, pressure, to perform some simulations until equilibration is reached. Then after that, to perform further production simulations to collect averages and positions, and then to analyze the results. The main and perhaps the most important input of molecular simulations of MOF is the force field. It describes the physical and chemical interactions between gases and MOFs. At the early stage of molecular simulations of MOFs, force fields specific to gas MOF interactions were developed first by using quantum level calculations. Molecular simulations which employs either universal force field or drying already showed good agreement with the experimentally measured gas uptake, especially drying, but less universal force field. Which makes this force field useful for the modeling gas absorption inside these MOFs. And what is force field? It is a collection of equations and associated constants which are developed to reproduce molecular geometry and selected properties of molecules. Force field modeling is based on Born-Oppenheimer approximation, and in a force field method, we explicitly treat electrons, and we calculate the energy of the system as a function of the nuclear positions only. In this graph slide, I show you the energy force field energy expression that can be used for MOF, and where the total energy consists of bonding and non-bonding term. Many force fields use harmonic potential for bond stretch term, or use some higher potential like Morse potential, which is more expensive. And in this equation, Kr and R0 are force constants. R0 is like natural bonds, and this is the term that calculates the strain of the system when bonds are different from the natural bonds. The second term is related to the deviations of the angles, where quadric polynomial term is sufficient, but also higher terms can be used. Force field parameters here k theta and theta 0 as natural angle. Then for the description of the torsions, a periodic function, cosine function can be used, that is presented here. Here n is a periodicity, it is number of the minima, number of the peaks and walls during the path, and parameters are k phi and phi 0. These four terms are bonded terms, but besides those three terms, the fourth term can be out of plane bending term, which can allow us to enforce planarity around some sp2 atoms. Non-bonded terms are mostly important and more important when you have some rigid framework. And we mostly had to develop these charges for our systems that we modeled. To describe electrostatic interactions, someone can use Coulomb law with placing partial charges on the atoms, interacting through the distance, which is labeled Ri. And also for the description of van der Waals interactions, we used Lennard-Jones 12-6 function, where here in this equation, epsilon is well depth, and sigma is the distance when the energy is equal to 0. For more accurate representation of the potential energy surface, for example, for vibrational frequencies, it is necessary to introduce some cross terms, which are presenting interaction terms between stretch, bend, and torsion. So how we perform molecular force field parameterization? We perform it by iterative adoption of force field parameters by performing molecular simulations and fitting them according to the mostly experimental data. As more as you have is better, to the experimental adsorption isotherms or experimental elastic tensors or some other properties, but also ab initio data can be used for the force field fitting. Besides the parameters for MOF, someone also has to define parameters for the guest host interactions that are non-bonding interactions, electrostatic and van der Waals interactions. For modeling sulfur dioxide or carbon dioxide inside the MOF, transferable potentials for phase equilibria, which is already developed, can work fine. It maintains a high degree of accuracy in the prediction of physical properties when applied to a range of different compounds. And this force field has been parameterized based on experimental phase equilibrium data. In this table are presented some of the parameters for the carbon dioxide charges and the parameters necessary to calculate the van der Waals interactions. Carbon dioxide and sulfur dioxide or hydrogen sulfur can be modeled as a three-site rigid molecules with charges on each site. Unlike interactions can be used can be defined by using the Lorentz-Berthold combining rules. Now I would like to shift to the explanation of the practical example of how grand canonical Monte Carlo simulations can be set up in the program RASPA, which we use for our simulations, which can be useful for the students. So on the left is the main input file called simulation input, which contains all the simulation parameters. First, we need to specify the simulation type, such as Monte Carlo or molecular dynamics, and to define the number of cycles. Here, it is 5,000 for initialization or equilibration, and for production, 15,000, but you usually need more. Next, we define the force field that describes the interaction between the framework and adsorbate molecules. So there is some section which is related to the framework. So the framework name means the coordinates of the MOF. Then you also need to define the unit cells and mostly simulations can be performed for MOFs by using supercell dimensions 3, multiple 3, multiple 3. Then you also have to specify some thermodynamic conditions. In this case, the temperature is 300 kelvins and the pressure is 1.325 pascals. Then you have to specify the gas molecule. In this case, is carbon dioxide. The adsorbate can have several moves in Monte Carlo. For example, molecules can do translation, rotation within the pores, and in a full grand canonical Monte Carlo simulation, insertion and deletion moves are also included. Allowing the number of adsorbed molecules to fluctuate according to the specified pressure and temperature. Then on the right side, we see the files needed to run RASPA code. Typically, we need simply run script that launches the simulations and the simulation input file that I just described. Computing adsorption isotherms. So basically, you need these three files: force field file, beside those that I mentioned. It contains the force fields, full force fields for if the MOF is rigid, you need just to define the non-bonding parameters for describing electrostatic in van der Waals interactions. Then framework, for framework, there is a file which is related to the structure of MOF. So here you can place coordinates from X-ray data, or you can optimize by DFT your MOF and place the DFT optimized coordinates. And also for the molecules, guest host molecules, there is a file which is called molecule name def, which also contains some information about the hosted molecules. Okay, so now I will shift to the examples how we perform this simulation. So as I mentioned, we first perform simulation in MAF 66. So this is the basic organic ligand of this MAF, which is called amitrol with one NH2 group. We change also this NH2 group and design new MOFs. The first MOF that we designed was MOF when we change NH2 with hydrogen in order to get more accessible pore size, which we label ZTF. So we were interested in the MOFs that can be very good absorber for carbon dioxide, first of all. And after we go further and change this NH2 group with actually in position 5 here in this amitrol, we introduce new NH2 group. So we design MOF with two NH2 groups, and then we substituted these two NH2 groups with two chlorine, and then perform the grand canonical Monte Carlo simulations to check if these MOFs are good carbon dioxide adsorber. So prior to grand canonical Monte Carlo simulations, we perform detailed DFT study of the interactions between carbon dioxide and zinc triazolate complexes. We optimize all possible isomers and tautomers of these zinc triazolate complexes together with the carbon dioxide in the different positions and obtain the stable structures presented on the left side together with the binding energies that are calculated at DFT level of theory, which includes dispersion. And we observed in all cases that the most stable structure are those with the covalent, where covalent bond between zinc and oxygen is of carbon dioxide is established. We also perform some calculations in PCM and water solvent, where binding energies are slightly changed and the ratio of the isomers is also slightly changed. And we obtained that this difference is because this zinc oxygen distance is larger in the presence of the water, since this bond is weaker. Besides covalent bonds, we also establish some sigma type hydrogen bonds between corresponding the groups of the triazolate complexes and carbon dioxide. So some weak interactions we observed. How we further do with the newly designed MOF and also the MOF 66, we had to optimize their structures by using periodic DFT calculations with Siesta. And on the left side are DFT optimized structures of the MOF 66 and newly designed MOF ZTF which possess two hydrogen inside the pores and has more accessible pore surface. We also perform DFT optimization of the two new MOFs, which we label ZTF1 on the left, with two NH2 groups inside the pores of MOF, and on the right side we substituted these two NH2 groups with chlorine, and this MOF is labeled as ZTF2. In this table, I present some structural parameters for MOF 66 and ZTF, together with experimental data for MOF 66. We observe very similar values of the unit cell parameters and angles for MOF 66. And in comparison with experimental data, here are shown also some binding energies between carbon dioxide and MOF that has been calculated with Siesta and using periodic DFT calculations. We calculate with RASPA code helium void fractions and surfaces area. So here you can see that newly designed MOF have higher surface area, suggesting that this could be better adsorber for carbon dioxide. Here are shown some DFT calculations of the adsorption carbon dioxide inside the newly designed MOF ZTF1 with two NH2 groups and with two chlorine, where we observed that binding energy, calculated binding energy, was higher when carbon dioxide is adsorbed in MOF with two chlorine atoms. Since chlorine is more polarized and can enhance quadruple interaction between the carbon dioxide and the MOFs. In this slide, I will show you now some results of the ground canonical Monte Carlo simulation. So inside the MOF 66 and ZTF newly designed MOF at the three different temperatures at 253, 273, and 298 kelvins. Isotherms which are labeled in blue lines are experimental data, where first we had to develop our own charges for these systems based on this experimental data that we had based on experimental absorption isotherms, and we good agreement between experimental data and our simulations absorption results. And afterwards we performed adsorption of carbon dioxide inside new MOF. The dots that are presented in the red, and what is very important, and that ZTF has higher adsorption properties properties than MAF66. So it absorbs carbon dioxide about 8 millimole per grams or 174 square meters per gram, whereas MAF66 absorb 142 square meters per gram or 6.5. This is just another unit, 6.5 millimole per gram of MOFs. In this graph, I show you now some snapshots from extracted from Grand Canonical Monte Carlo simulations, where we observed in MAF66 and ZTF only weak interactions, some hydrogen bonds between CH group of hydrogen-like bonds between CH group of MOF and oxygen of carbon dioxide, or between NH2 group and oxygen of carbon dioxide. By performing the same simulation methodology, we also calculated the absorption of carbon dioxide inside the newly designed MAF ZTF1, and this is MAF with two NH2 groups. We expected that this MAF can increase CO2 absorption because there are two NH2 groups that can interact with carbon dioxide through stronger hydrogen bonds, but due to the due to some steric interactions or due to the bulky NH2 groups, the space inside the pore is more occupied with NH2 groups and cannot absorb enough carbon dioxide. So for this MOF, we observe some very modest absorption properties, which are, for example, at 273, about 3 millimole per grams. Whereas when we have two new MOF with two chlorine atoms, when we substitute chlorine with NH2 group, we observe better absorption properties, which are about 5 millimole per grams at 273 kelvins and 1.2 atmosphere. So this is also expectable since chlorine is highly polarizable and can enhance quadruple interactions with carbon dioxide. From the Grand Canonical Monte Carlo simulations, we also extracted some snapshots in order to analyze the interactions between hosted molecules and MOFs, and we observe again some weak interactions between some hydrogen bonds between NH2 groups and the oxygen of carbon dioxide, and some weak electrostatic interactions between corresponding groups. So in conclusion, for this part, carbon dioxide absorption in MOF is controlled by a balance of surface area, pore size, accessibility, electrostatic interactions, and also someone can include the framework flexibility. So in conclusion, the best absorber is the one with two hydrogens inside the pores, which allow the more accessible surface for carbon dioxide absorption. We also go further, and we were interested how our MOFs can absorb highly toxic sulfur gases like hydrogen sulfide and sulfur dioxide. Absorption of sulfur gases is a very challenging task since sulfur gases can form some irreversible bond between sulfur and metals and can disturb the structure of metals. So we here had to check our MOFs if their structure is destroyed by upon absorption of sulfur dioxides and or hydrogen sulfide. The same like before, we performed the calculation of binding energy between sulfur gases and our newly designed MOF, where we observed the very the binding energy which are in the range of for sulfur dioxide 7.4 kilocal per mole, whereas for hydrogen sulfur is 13.5 kilocal per mole. For the adsorption properties, we were very satisfied. The adsorption properties of newly designed MOF and MOF 66 showed even better adsorption properties in comparison with carbon dioxide, which are about 223 centimeter on cube per gram of MOF for MOF 66, whereas for the ZTF MOF, they are very similar. Like with MOF 66, it's about 220. And the same we perform with ZTF. I already said that they are very good, so I will just skip this slide. For the snapshots from Grand Canonical Monte Carlo simulations, we were able also to observe some metal oxygen bond between metal zinc and the oxygen of sulfur dioxide, and not any bond that can disturb the structure. We go further in the describing absorption properties of sulfur gases, and we also placed water molecule inside this MOF at two different positions near the nitrogen and near on the left and near the zinc on the right. From the Grand Canonical Monte Carlo simulations, when we have inside newly designed MOF ZTF, sulfur dioxide absorption besides water is reduced in all cases. Whereas when we have hydrogen sulfide, we have two regimes. For the pressure less than 0.6, our the absorption of hydrogen sulfide is decreased, which is acceptable due to the competition with the water, besides the water. Whereas when the pressure is higher than 0.6, the absorption is slightly higher. It means that presence of sulfur gases, hydrogen sulfide can increase some interactions between the presence of water can increase some interaction between sulfur gas and the MOF. We also perform simulations of the sulfur absorption of sulfur gases beside the carbon dioxide, and in all cases we observed that the presence of carbon dioxide decreased the absorption of sulfur gases due to the competition factor. So now I will just show you the final results, which are related to the CALF 20. CALF 20 is composed of layers of 1 to 4 triazolate bridge zinc 2 ions, which are pillared by oxalate ions to form a three-dimensional MOF. Zinc in this MOF is 5 coordinated with distorted trigonal bipyramidal geometry, and there are no open coordination plates. CALF 20, which we denoted as alpha CALF, which is very important for the absorption of the carbon dioxide, even in the industrially relevant conditions. When it is exposed to the humidic conditions, can generate a new polymorph, which is called beta CALF, and this alpha to beta transformation is usually reversible. So for the modeling absorption inside beta CALF, only computational data can be performed. And this reversible transformation also leads to some structural transformation between the when going from alpha to beta CALF, then the structural changes are from going from bis bidentate coordination, which is present in alpha CALF, to have more bis monodentate coordination, which is present in beta CALF. which suggests a reduction in the zinc coordination number. So here we firstly optimize the structure for both alpha calf and beta calf, presented here on the left and on the right by using again the siesta code and periodic DFT calculations. Here are some structural parameters for calf 20, alpha and beta, together with available experimental data, where we observe very good agreement with experimental data. And we also calculated the helium void fraction and surface area. From surface area, you can see that they are similar, which suggests that both polymorphs can absorb very good carbon dioxide. For this system, what is the most important, we develop new charges, new force fields, and use the drying force field for calf 20, whereas for carbon dioxide, since we had the problem to fit experimental data during the whole pressure range, and then when we shifted to Garcia Sanchez force field for carbon dioxide, we were able to perfectly reproduce experimental data. And this is some basic workflow how to develop force fields. So you have to set up initial structure, both MOFs and carbon and hosted molecules, in this case carbon dioxide. Then you have to do atom type assignments to calculate charges based on the DFT level of theory, in our case in the DFT PB level of theory, and then to perform ground canonical Monte Carlo simulations and to validate them by using in an iterative manner until satisfactory agreement with experimental data. As an output, you can get adsorption isotherms and detailed pictures of the interactions between the hosted gases and MOFs. On the left side here are isotherms of that we obtained with the ground canonical Monte Carlo simulations at 3 different temperatures. So we extended the temperature range since we had a lot of experimental data, since this MOF is very well studied due to its great application in the adsorption carbon dioxide. And we observe very, very good agreement with the experimental data. The diamonds, open diamonds are experimental data for all temperatures. For example, at 293 kelvins and 1.2 atmosphere, the simulated absorption is almost 4 millimole per gram, whereas experimental value is 4.183 millimole per grams. On the right side are the radial distribution functions that are obtained at 3 different pressures, at 2 different pressures. Here you can see that we have 3 peaks, one which is related to intracavity pairing between carbon dioxides, and 2 peaks which are related to intercavity pairing. This method also confirms cooperative 2-step filling mechanism, where initial single occupancy of cages is followed by intra-cage pairing. Here are some results of carbon dioxide absorption inside alpha calf, where we observe only weak interactions, some hydrogen-like bonds between CH and oxygen of carbon dioxide, and electrostatic interactions between metal and oxygen of carbon dioxide, or oxygen of oxalate ring and carbon of carbon dioxide. We also perform a simulation, ground canonical simulations of absorption of nitrogen inside this MOF in order just to check our force field. We observe very good agreement. And further, we extended our simulations with some analytical ab initio thermodynamics method, which combines periodic DFT, DFT-D method with MP2 corrections for to calculate absorption energies, and non-isolated site term to capture some non-local effects. And this non-isolated site model was developed by our collaborator Kaido Sillar from Estonia. And on the right side, you can see excellent agreement between all the methods that we use. So two methods and experimental data, which are the accuracy is in the ratio of chemical accuracy. All the investigated properties were below 4 kilocal per mole, or even less, 1 kilocal per mole. For example, we calculated some thermodynamic functions, and these are these values are calculated by using isolated model, non-isolated model, canonical Monte Carlo simulations, and all the data are compared to experimental data. The first part is related to the absorption of 1 carbon dioxide, and the second data are related to the absorption the second carbon dioxide inside the MOF, where we, for example, for Grand Canonical Monte Carlo, by absorption of 1 carbon dioxide inside the MOF, we observe very good agreement with experimental data for absorption enthalpies, entropies, and Gibbs-free energies. Whereas for the absorption another carbon dioxide molecule, these capacities are higher than 1 kilocal per mole. They are about 2 or 3 kilocal per mole, which can be due to the flexibility of MOFs that we did not take in account. We choose rigid mode. But anyway, the results are in excellent agreement with experimental data. We also perform simulations for the beta calf, and we, as expected, we observed that beta calf is very good adsorber with the absorption of which is equal to 3.7 millimole per gram at 293 kelvins, which is similar to alpha calf. From the non-bonding interactions, we observe also similar interactions like with alpha calf. So this beta calf can also be used to absorb carbon dioxide in the humidic, more realistic conditions. But the only problem is that this transition between alpha and beta calf is so fast. So until now, alpha calf is superior in the absorption of carbon dioxide. For visualization porous materials, I would suggest IRAS code. With this link, you can download it. It is free of use, like RASPA code also. So main features of iRASPA are structure creation and editing, creating high quality pictures and movies, cell replicas and supercell, symmetry operations like space group and primitive cell you can detect, and you can compute also void fraction and surface areas. So with this, I would like to finalize this talk to conclude. So basically, the equilibrium structures, bonding, and the stability of carbon dioxide and zinc triazolate complexes in gas phase and water solution have been studied by DFT with the inclusion of dispersion corrections. So we used an in silico methodology to design a new MOFs by modifying the well-known MOF 66, targeting better carbon dioxide absorption capacities with and without the presence of water. So we have shown that MOF 66 and ZTF family of MOF, and also CALF 20, composed of triazolate or triazolate oxalate based organic ligand and zinc 2 ions as metal ligand have an exceptional carbon dioxide absorption capacities. And also MOF 66 and ZTF are promising candidates for the capture and removal of sulfur gases, some toxic sulfur gases from air. And also new polymer beta calf also may have an important role in capture carbon dioxide in humidic conditions. At the end, I would like to thank to my collaborators, to Majdi Hoskla from University of Paris and his PhD students, Rahma Dahmani and Narahali. Then I would like to thank to Kaido Silar and to my ex-PhD student, Ivana Georgievich. And I would like to thank to Cozy Action, which supports our collaboration, and also Section EU for MOFs. And I also would like to thank you all for the attention.
Thank you very much, Sonja. Let's thank our lecturer. And now we have some time for questions. Please, if there are any questions in our room, in Zoom, please raise your hands. Maybe we are. Yes, there is a question. Please.
So, Sonja, thank you very much for the very exciting talk. And I have actually a pretty silly question, but maybe I missed this. But you say that you use the canonical ensemble, and in this ensemble, so the number of particles can change. And if you know that in molecular dynamics we have the constant number of the particles and all the boundary condition, but I don't understand in your simulation where the particles go and from where they come. So do you have some reservoir or something like this?
I had the same silly question.
So in the grand canonical ensemble, the number of particles is allowed to change because the system can change particles with the reservoir. Particle can be inserted into the simulation box from the reservoir and then can be also deleted. So they can be inserted and deleted, and based on the Metropolis algorithm that I showed, the only new configuration with lower energy can be accepted. Otherwise, they are deleted.
And also, returning back to this question, this is we have to fix constant chemical potential. So the number of particles changes, but the chemical potential is constant.
Yeah, chemical potential has to be fixed. Yes, and
it is somehow is
the number of particles is allowed to fluctuate.
So the number of particle changes. Okay.
Thank you.
Thank you. And other questions? Maybe I ask question just maybe more technical or more to this problem of simulation within the framework of this method, and also what is related to metal organic framework. So you consider actually very small volume. So this is metal organic framework. This is a small molecular cell with some molecules inside. And you do this Monte Carlo simulations for such system and for one molecule inside, actually, as I correctly understood.
Yes, but we have a lot of pores inside.
So you consider a lot of pores and also a lot of...
the pores of the MOF provide the available volume where gas molecules can be absorbed, and the surface of MOF is extremely high, as I show in the beginning somewhere, I don't know, that it is, for example, for this MAF5, the surface is almost 4,000 square meters per gram. It's like a football... it's in this slide. It is like a football pitch packed in just a few grams of material. So MOFs have the highest of surface area of any known material. And they are very useful for adsorption of carbon dioxide for this large scale production, which is very important in industrially relevant conditions, and also for absorbing the water due to their interactions with water or carbon dioxide. You can change to substitute the groups inside the organic linker, and then you can get MOF, which can absorb very well carbon dioxide due to some interaction. For example, for our CALF 20, we only observe that mostly dispersion interactions are observed with this thermodynamic method, ab initio thermodynamic method. We calculate that only weak interactions are present inside when adsorption of carbon dioxide is present in CALF 20, which is also interesting. And this material is won a Nobel Prize. I mean, the Nobel Prize laureates were won the Nobel Prize based on the developing this MOF, besides the many other MOFs.
I see. And also I wanted to ask about molecules of hydrogen, H2. So did you
sorry, I didn't understand.
molecules of hydrogen. So you consider carbon dioxide, but maybe hydrogen molecules you also can consider as molecules inside these MOFs.
Yeah. Also, hydrogen can be adsorbed. I showed also the one MOF here, which is good, which is labeled new 1501, which can also.
I asked because, as I understand, this is from practical use, so this is very important to adsorb hydrogen to some small volume, and after that to extract this hydrogen for some use, and it may be useful in this way, MOFs. So this, yes, we can see.
I didn't understand your question about this hydrogen. I mean, MOFs can be used depending on the structure. They can absorb different gases, so you can change the structure upon your application.
Yes, I see. I mean that you didn't study.
I still didn't study adsorption hydrogen gas. It's only carbon dioxide beside the water or without water. So this sulfur gases until now. But I plan to extend this research.
Okay. Thank you. So, dear colleagues, other questions? No questions in our room and maybe in Zoom. Are there any questions? Okay, no questions. So, Sonja, thank you very much for very interesting lecture. We enjoy, and let's thank our lecturer again.
Thank you for the invitation.